So we have covered almost everything in DC motors. We are left with two topics that we need to cover: DC motor starters, and secondly we'll be studying Ward Leonard system. Uh, as far as the DC motor starters go, why do we need the DC motor starters? We basically require the starters for mainly for prevention of the DC motor against excessive starting current. The starting current of a motor is very high. Using an example, I'll be just showing you that. We want to protect our DC motor against the damage that the starting current, that the excessive starting current will cause to it. And for that we need certain mechanism to limit the rise of the starting current. And for that purpose we'll be using starters. Besides this, the starters can also be used for prevention against short circuit. So for example, there was a short circuit in any electrical part of the circuit, and we are using starters to basically start it. Since the current will be limited, it will not cause any, you can say, major damage to the motor in case we were directly starting the motor instead of starting two DC motor starters. Also, it can protect against overloading in case the machine has been overloaded. You can use a starting mechanism to prevent against overload voltage and current. As we can see from this example, we have a DC motor here. Its rating is 50 HP and 230 volts, while as the armature resistance of this motor is 0.02 ohms. You can say the combined resistance, the combined internal resistance, if this is a series motor, the armature resistance plus the field resistance is 0.02 ohms. Right? The internal resistance of the armature windings is realized equal to 0.02 ohms. So what will the current in this motor be? As we know, I is equal to Vt minus Ea divided by Ra. The value of Vt is 230 volts. The starting current, we are talking about starting current, right? This is starting current. So at the start, the armature has not yet rotated, the rotor is not rotating. Ea is equal to k phi omega. Since omega is equal to 0, therefore Ea is equal to 0. So Ea is 0 here and Ra is 0.02 ohms. So approximately this is somewhere around 11,000 amperes. Fine. So you can see the starting current is very large. It is of the order of 11,000 amperes for a simple motor of is for a simple 50 HP motor. This current is very large. You can say for this motor the rated current could have been somewhere around 40 amperes. So this is almost 30 times more than the rated current of the motor. That actually causes that will cause a lot of damage. That will cause the motor to burn completely actually, because this excessive current is very large. So we cannot directly start the motor. We cannot directly apply the terminal voltage equal to 230 volts and expect the motor to run normally. What we need to do is we need to basically either control this Vt, fine, so that we can actually raise this voltage from 0 to 230 volts slowly. Fine. Meanwhile, while we are actually raising this, speed will also begin to increase from 0 to rated value. As speed will increase, Ea will also increase. Since Ea is increasing simultaneously with respect to Vt, in such a case where we are raising the voltage from 0 to 230 volts, therefore what will happen is that our starting current in this motor will be limited. Or the second method what we can adopt to limit the starting current is use a starting resistance in series with the armature resistance. This starting resistance, say for example, again this will be a variable resistance. So let's say it has our start is variable, and we can change its value from 50 ohms to 0 ohms. Fine. So when we are applying say 50 volts, 50 ohms resistance at the start, the current in that case will be limited. It will be only 4 amperes, and we can gradually decrease this resistance from 50 ohms to 0 ohms, so that the starting current is reduced and the motor is also becomes operational while we are reducing this, while we are maintaining the low starting current. Now the question here is, can we keep the starting resistance permanently in the circuit? The answer is no. Having a resistance permanently in the circuit means that there will be considerable power losses, because there will be continuous I square R losses through the starting resistance, and secondly it will affect the torque speed profile of the DC motor. The torque speed profile will also decrease. Now what type of starters do we have? In literature you will see two different types of DC motor starters. One is the manual starter. A manual starter is simply a device where human operation is used to change the resistance that's actually connected in series with the armature. You can see this resistance here. So you can connect it at this point, at this point, at this point. Accordingly, the full resistance, and at last, at the last point, you will make sure that your resistance is 0, this starting resistance, while as the armature resistance in this circuit will remain as such. So this manual operation a human operator can use to vary the resistance. Say for example, you might have seen a rheostat also, a rheostat in which you are simply sliding. You use simple slider to basically change the resistance value, or you can even, as you may have seen in case of old fan regulators, where we are basically changing steps, those were actually also resistances being incorporated. Those resistances were actually being incorporated from step 1, step 2, step 3, step 4 to step 5, as we have seen in case of old fans at that nowadays we have continuous variable regulators pots being used in fans, but in old days we use simple resistance based switch to change between different levels and incorporate different values of resistance in a fan. The purpose of using resistance there was different. The purpose of using resistance here is different. We are using this resistance for starting purpose, so that we can limit the starting current and make sure that the motor does not burn because of the excessive starting current. Now obviously human operation has limitations. We cannot be exactly human operator cannot exactly match the transient behavior of operation. Fine. If the human operator goes too fast, the starting current may not have yet reduced by considerable amount. The speed may not have yet built up completely to produce a sufficient amount of EA. The starting current will still be very large, and that may cause damage to the motor. Secondly, if the human operator goes too slowly, it may leave the resistance in the circuit for too long. That may actually damage the resistance itself and then cause considerable amount of power losses. So instead of using manual starters, we can go for automatic starters. In automatic starters, what we are doing is we are actually operating these contact points, and say for example, initially all of this resistance was incorporated in this motor, and the current will be flowing through this path. Secondly, in the second step, what we can do is we can close this first contact IA, so that current flows in this path like this from the minimum resistance path, and then we can operate to A as well, so that current flows through this path. And finally, when sufficient amount of speed has been achieved in the motor, that builds up EA sufficient amount to limit the starting current, we can operate all the starting contact points so that current flows through this path and none flows through the starting resistance, and we are actually able to disengage the starting resistance. And we need to disengage the starting resistance because we cannot place it permanently in the DC motor moving to these regions. Now, how to basically go for automatic operation? We have two approaches, and one approach is this approach is time delay, time delayed relays. In this approach, we are using time delayed relays, and they are actually operated like this in the circuit. So what are relays? Relays are actually energized as relays are normally open. As soon as they are energized, they close contacts. That's the normal operation of a relay. But in case of time delayed relays, they will close contact but after a certain time delay. So we are using 3 different time delayed relays and in 3 different settings. We can keep actually relays have the ability to be, there are multiple settings in the relays. We can go for plug setting, we can go for plug setting in relays, we can go for timer settings, and you will actually be studying these relays in cost and protections, and you will be studying how we basically go for different settings. Here you need to understand only the fact that we can use relays, time delayed relays. They simply operate, they close when they are energized, and in case, since they are time delayed, they will close after some interval of time. We can set that time in the relay so that 1 TD close after, say for example 0.01 seconds, 2 TD will close after 0.02 seconds, 3 TD this relay will close after 0.03 seconds. So accordingly, the starting resistance will be disengaged in the motor. That's actually incorporated here. Fine. So this schematic here only shows the contact of how to basically connect this 1 TD, 2 TD and 3 TD in the circuit. This M here represents a push button. So as soon as the push button is actually pressed, the motor will be energized through the starting resistance. Initially the current will be going to R start, the current will be limited, and there are other protection devices in the circuit, like you have these F1, F2, F3, F4, the fuse in the circuit. You have protection against overload, fine. And what else? You have also FL here. This is again a relay used for protection of the field circuitry. So this is one approach. In the second approach that we are using here, you can see we are using again relays. The difference here being is that these relays are not operated by the terminal voltage. In this case, these relays 1 TD, 2 TD, 3 TD, they were energized from the terminal voltage. But in this case, these relays are operated by the energy energized by the EA that basically builds up across the motor. So the operation will be similar. One AR will be, instead of being operated by the terminal voltage, these relays are being operated by EA, and the operation will be similar. 1A will be closed first, 2AR will be closed second, 3AR will be closed third. Why this is more efficient? Because the source of energy here, because we'll be exactly able to monitor how much amount of energy is being built up across EA, how much, depending upon the loading of the machine, depending upon the rotation, speed of rotation of this machine. So this method is much more better. The rest of the circuit elements are same. We have overload protection, fuse, relays for field protection, extra. So this is about starting DC motor starters. Secondly, we need to discuss about Ward Leonard system. In the Ward Leonard system, this is actually a speed control strategy. We have studied different speed control strategies of DC motors. We discussed the armature control strategy and the field voltage. So in armature control strategy, we studied that we can control the armature terminal armature voltage, armature voltage input to the DC motor, so that we can control the speed of rotation. Or in the field control strategy, we can control the field current and therefore the flux. Armature control strategy can be used for control of speed from 0 to rated value. The field control strategy can be used for control of speed from above the rated values. Ward Leonard system, it's mainly a armature control strategy, but we can also incorporate field control strategy within this system for four quadrant operation. Now, why we are studying Ward Leonard system? Ward Leonard system basically has been used in industry setups for a lot of time, and it has been one of the most efficient. It was one of the most efficient speed control strategies, and because of a number of advantages that have been listed here, you have wide control range. You can control from 0 to rated value, and you can control even above the rated value using the Ward Leonard system. And you have the possibility of control of the motor in all the four quadrants, as we explain the four quadrant operation shortly. As you can see at the figure, you have G1, it's an AC generator. We have G2, it's a DC generator. We have G1, we have G2, and we have this motor M, whose speed we are actually controlling. So as you can see, the AC motor, you can control the speed of this motor by controlling the speed of this generator G1 of the AC motor. So once we control the speed of this motor EA, that's actually equal to K phi omega. Fine. We can either vary the flux of this generator, or you can vary the speed of rotation of this motor. In either case, EA1 can be changed. This EA1 is actually connected to the terminals of this DC motor. So you can actually control the terminal voltage, or what is known as the armature input voltage, to the DC motor, so that you can control the speed of this motor. So this is the simple operation of this Ward Leonard system. You are having two extra machines to control the speed of a DC motor. Now, what are the advantages of this? We can operate it in all the four quadrants. This here shows a four quadrant operation. What this basically means, this is the first quadrant, this is the second quadrant, this is your third quadrant, and this is your fourth quadrant. These are torque speed curves in different quadrants that have been given to us. What exactly this means is, in the first quadrant operation, what we are doing is we are simply we are actually controlling EA1 by controlling the speed input to this generator, so that terminal voltage will be controlled. Terminal voltage that's developed here is having the polarity like this, VT plus minus. Current is flowing into the motor. We'll assume that current into the motor is positive. So in this quadrant, VT is having positive polarity, and current is having positive polarity, is also positive. And we know V is voltage is proportional to speed, and torque is proportional to current. So if V is positive, that means speed will also be positive, as shown in this diagram. This is the omega versus torque axis, As shown from this diagram, you can see omega is positive in this quadrant, and since current is also positive, that means torque induced is also positive. So in this quadrant, the torque is also positive. This is normal motoring operation. It is known as forward motoring mode. Forward, it is motoring mode because if you look at power flow, power will be Vt into Ia. Since Vt is positive, Ia is positive, power will be positive. That means power is being fed to the motor. So therefore it is motoring mode because power is positive, and it is forward motoring mode because speed is positive. Now what happens in the second quadrant? In the second quadrant, if say for example you were to change the flux of field, you were to induce, you had a separate field control again for this motor M, so that you can decrease the flux of this motor. If you decrease the flux, not decrease the flux, if we are able to basically increase the flux of this motor, if we are able to increase the flux of this motor by increasing the field current, EA2 will basically increase. EA2 is also proportional to its flux, its own flux, that is phi 2, say for example. Since we are increasing flux, EA2 will increase. The voltage from this side is still positive, plus minus, but since EA2 is now, we can increase the flux so much that EA2 becomes greater than Vt. Since EA2 will become greater than Vt, the current will now start flowing in this direction. So in this quadrant, what happens? Vt is still positive because we have not done anything with the terminal voltage that was being applied to the motor. But current has now reverse direction. And why has current reverse direction? Because we have increased the flux input of the motor, and that increases its voltage and the potential. And the current law states that the current will flow from higher potential to lower potential. Therefore, omega is positive here. The torque is negative. So you can see in this quadrant, torque is negative, but omega is still positive. What will power be? Power will be Vt into Ia, that will be negative. Negative power means now power is not being supplied to the motor. The motor is actually supplying power. That means this motor now becomes a generator. So that's why it is a generator operation. And since speed is still positive, it will be known as the forward generating mode, or it's actually referred to as forward regeneration mode. Fine, because this is not a normal operation. Or a normal operation is it's a motor, but we are making it as a generator, so it's known as regeneration. So this is your second quadrant, how it actually operates by changing the field of your motor circuitry. In the third instance, what we can do is now going back to the normal flux that we had. What we can do, you have the generator 1, generator 2, you have this motor. Now in the third quadrant, what we'll do, we'll change the flux field of this motor so that it develops a negative voltage. The voltage developed here will be plus minus like this. So now we are applying the field control of generator 2. We'll be able to reverse, or we can actually reverse the speed of the motor also, reverse the speed of this AC motor, right? So that this generator will produce a negative polarity based voltage. Since we are now producing a negative polarity voltage, current will flow in this direction. So this is in phase opposed manner to the earlier convention that we had obtained. So in this mode, VA is negative as well as current is negative. That means both speed is negative as well as torque is negative. With both speed and torque negative, power will be positive, because negative into negative means it's positive. Power being positive means it's a motoring mode, but since speed has become negative, it will be referred as reverse motoring mode. So what happens in this mode is that we are able to operate the motor, but in a counterclockwise. If earlier it was operating in a clockwise direction, now it will be operating in a counterclockwise mode. And finally, we again control the field of motor M2 so that its voltage is greater. Now it will be also producing a voltage of polarity plus minus like this. Once this supplies a negative polarity, it will also produce a polarity of this magnitude. Now if we change its flux so that A2 becomes more, IA will flow in this direction. That means now in this mode finally we'll be having a negative voltage but a positive current. That means omega is negative but torque is positive. That means power is negative. Since power is negative, it's a generating mode, and since speed is negative, it's a reverse generating mode. So this is 4-quadrant operation. So this is possible to be achieved using Ward Leonard system. However, nowadays this method is no longer used, owing to obvious disadvantage, because we are using two motors of similar rating to that of the motor to control one speed of one motor. So obviously it has more cost, it's more costly, as well as it's less efficient, because more machines in a system means less efficiency, and less efficient device, because there will be more power losses, collective power losses will increase, it will be a less efficient device. Having said that, nowadays we are actually using solid state devices, using rectifiers, using choppers to control the motor speed, and it's possible to control the motor speed in a 4-quadrant, in all the 4 quadrants easily using choppers or rectifiers. That you'll be studying later in your power electronics course. So this is all for DC motors. We'll be starting with DC generators in the